This is our third application of basics right triangle trig. From a given point on the ground, the angle of elevation to the top of a tree is 36.7 degrees. From another point that is 50 feet further away from the tree than the first point, the angle of elevation to the top of the tree is 22.2 degrees. Find the height of the tree. This is an incredibly practical problem. This is just type of situation occurs in surveying and measurement all the time, where you can use trigonometry to find the height of a tall object without actually ever measuring how tall the object is, right? You don't have to, it's not like you have to climb to the top of the tree to figure this out. So here's the ground. We got this tree. And what we're saying is from a certain point on the ground, the angle of elevation to the top of the tree. Now I got to make sure one side is horizontal for an angle of elevation or an angle of depression. I don't think you'll be tempted to do the wrong thing here, but I'm just pulling out my yellow card just to remind you that whether it says elevation or depression, one side must be horizontal. So this right here, 36.7 degrees. And then we're saying from another point that is 50 feet further away from the tree. So we're going to move 50 feet back, and then we're going to measure an angle of elevation, which you can do with a surveying kind of sextant tool. 22.2 degrees is that angle. And we want to find the height of the tree, right? So I'm going to call that x. So this is just to me, again, a great practical example where we don't even get close to the tree. We just measure these two angles and the distance between where the measurements were made, and we can use trigonometry to figure out the height of the tree. So cool. All right. Now, right now we have certain constraints on how we can solve a problem. We need right triangles, and we don't know how to work with triangles that are not right triangles. So for example, this kind of obtuse angled triangle right here, this piece, we can't work with that triangle because it's not a right triangle. We don't know that it has a right angle. We are assuming that there's a 90-degree angle right here in our picture. And I see a right triangle here with the 36.7 degree angle, but notice for that smaller inside right triangle, we don't have any of we don't know any of the sides of that triangle. And actually, there's a larger triangle that goes around the outside. That's another right triangle where we don't know any of its sides, actually. We just have a piece of it. So what I'm going to do is I'm actually going to draw both of those triangles. I'm going to copy the larger one where there's sort of this line coming down there, and then the smaller one. So this angle is the 36.7 degrees, right angle here, x. This is x, this is 22.2 degrees, and then we have this piece of the base of that thing being 50 feet, right? And so what I'm going to do is I'm going to take an approach here that isn't the only way to solve this problem. There are many ways this could be solved. But what I'm going to do is I'm going to say I choose to introduce a second variable, a y, into the problem. X is the height of the tree. X is what we're trying to find. But if I introduce the second variable y, in other words, I'm going to call this side of that triangle y, then this length is also y, feet. And then the total base is going to be 50 plus y. We add those two lengths together to get the total. Now, if I now have two variables, so I need two equations. I'm going to have a system here. Okay, so I have two triangles, so maybe I can get two equations, one from each triangle. And actually, for this right triangle, I have the opposite and adjacent side labeled to 22.2 degrees. For the other right triangle, I also have the opposite and adjacent side labeled. So I can write down a tangent equation for each triangle. Tangent of 22.2 degrees is opposite over adjacent on this triangle. That's x over 50 plus y. And on the other triangle, tangent of 36.7 degrees is x over y. And so what I actually have two equations and two variables, and really at this point it's just a matter of algebra. Like if you've set it up, you've done the trigonometry portion of the problem, and all that's left to do is solving for x and y. Now it's there's no standard procedure that always works for this type of situation, but let's see what we can say. Now I'm also going to substitute in values for the tangents here and here. Now you could wait, you could work with these expressions and try to solve for x and y and go to your calculator at the end, or you can go to your calculator right at the beginning. I'm going to go right at the beginning. Tangent of 22.2 degrees is 0.4081. I get on my calculator. So I have rounded off at this point, and it's tangent of 36.7 degrees. I'm getting 0.7454. And because I've rounded off now early in the problem, I have a lot more calculations to do. It is true that if you round off early in a problem, you can wander away a bit away from the final answer because other calculations kind of cause you to drift. That's not an issue for us. That's perfectly fine. I definitely will give folks leeway in answers they get for this type of problem. I mean, there is one exact answer given the information, but you're not obligated to get that exact answer. Just be fairly close. I have to give some leeway because if you round off at different points in a problem, your answers will look slightly differently, and I mean very slightly differently. Okay, so now we got these two equations, and we have to solve this system of equations. And I guess when I see fractions involved and expressions with variables in numerators and denominators, a good strategy is just to clear denominators. I can multiply both sides of the first equation by 50 plus y, and I get 0.4081 times 50 plus y equals x. And in the second equation, if I multiply both sides by y, I get 0.7454y equals x. And I kind of like that because this looks a lot less complicated all of a sudden. Now, I also see, like, this sort of just falls out of the problem here. I have an expression equals x from the first equation. I have an expression equals x from the second. I'm gonna substitute the x here with that expression that's equal to x from the second equation. So I have 0.4081 times 50 plus y equals 0.7454y, substituting that in for x. I now have an equation with one variable that I can solve for y. Now, y is not what we're actually after in this problem. We introduced y as an artificial kind of variable, but that's okay. If we find y first, we can go ahead and figure out what x is, and that's the height of the tree. That's what we're ultimately looking for here. There is a way to go right to x too if you want to think of the algebra, if any of you are clever to think about dealing with the algebra, but I just don't think it's worth it. I think it's just so easy to solve for y here. I'm going to do that. Okay. So I think I'm just going to go right to a second sheet of paper. I'm going to copy this one equation, 0.4081 times 50 plus y equals 0.7454y. And in the rest of the steps to solve here for y should be pretty clear to you. I just want to make sure everybody knows. We got to distribute the 0.4081. That's going to be 20.405 plus 0.4081y equals 0.7454y. And now I can subtract 0.4081y from both sides, right? And I'll have just 20.405 equals, I gotta take 0.7454 minus 0.4081. I get 0.3373. And now to solve for y, I just divide and let's see, 0.05, and I get that y is about 60.495. So let's just say y is 60.5, and that was 60.5 feet, I believe. So I just rounded that y off to one place. And now we need x. That's the height of the tree we're looking for. So I'm going to go back to, really, I can go back to any equation involving x and y. The easiest one is probably this guy right here. I'm just going to recopy that. 0.7454. 7454 y is equal to x. So 0.7454 times 60.5 is equal to x. And I get about 45.1. Again, I'm going to round off at one place. There's the height of the tree. So we don't need the y value for our final answer. And again, there are other ways this could have been done, but I think this is sort of a cool technique. I'm just going to put the answer there. Let's see if I can get the answer with the setup at least for the final shot here.